Hello, ladies and gentlemen, and welcome to our unit on waves. In this unit, we're going to be looking at the nature of waves and how it transfers energy. And the best way to do that is to study light. So waves, we're going to break this unit into two. First, we're going to study the nature of waves and lights. And the next unit after this, we're actually going to cover waves and sound. It just seems to me that's an easy way to do it. But let's just go ahead and get started with waves. Here are our learning goals for this first unit, this first video. I want you to be able to identify where waves are used in the world. I want you to be able to identify the parts of a transverse wave. I want you to be able to explain how light travels, and it can identify the properties of a transverse wave, which also include amplitude and frequency. Slotted notes for this first section begins here. So if you would, go ahead and get your notes ready, and we will begin in just a moment. Here are the standards that we'll be covering in this first unit. We're going to be looking at the properties of waves. Actually, if you look at SPS 9, we're going to cover the standard 9 first, and then we're going to jump into the nature of sound and electromagnetic radiation. This unit is very interesting and it's very fun. To me, it's a way to know how energy moves throughout our universe. So I look forward to explaining this, and hopefully I hope you enjoy learning about this. This explains a lot of ways that we interact with the world around us and how the world around us interacts with us. So let's just jump right in. Now, the first thing I want to show you is a waves flow chart. Okay, so the first part of our flow chart is at the very top are waves. And as you can see, there's two arrows coming off. There's two types of waves. The first wave we're going to look at are light waves. Okay, now light waves can be broken down into two forms. Okay, you have transverse waves and you have electromagnetic waves. Okay, now I know that these are big words that are jumping out scary at you right now, but never fear. We're going to, as we go through this, we'll talk about it a lot, and you'll get a better, deeper understanding of what these mean. Okay, now the other part of waves that our next unit that we're going to talk about is going to be sound, and those actually move in longitudinal or mechanical waves. Okay, so this is a flow chart that you can look at to refer to say how does light move, how does sound move, and how do I interact with it in the real world. Now here's some words that you're going to hear throughout this unit. A lot of words that you may have never heard before, and we're going to look at them in depth. Something like wavelength or Doppler effect, amplitude, electromagnetic wave, refraction, reflection, wave speed, interference. Some of those you may have heard before, and you can apply that knowledge to this section. But if you haven't, then you're going to learn them in this section. So first of all, we're going to jump off and just start at the very beginning. Okay, what are waves? How do we know what waves are? Well, the waves are like we all know the surfer dude, like totally tubular. Let's jump in and do some surfing, man. That's totally what waves are. Waves are from the ocean. Okay, that's what we most recognize waves from. If you've been in a swimming pool or any body of water that you could jump into, you've probably had waves come at you, or you've made waves, ripples yourself. But not only waves are in water, they're also in light. We get them from the sun every day that the sun is out and that we interact with the sun. We get light from the sun. They're in our microwaves. Okay, that's probably, you go to the microwaves and, oh man, I want some mac and cheese. throw it in there, turn on the microwaves. Those waves move and carry energy to your mac and cheese, get them hot and bubbling. And then when it gets done, you take it out, mix the cheese in, boom, mac and cheese. So, and they're even in our cars. We listen to radios, okay? Waves bring us the music or the talk radio or whatever if you listen to the radio, you get waves to bring to your car. Now, this doesn't count for streaming. Well, I guess it kind of does. Yeah, it kind of does. Any kind of music you listen to, you get waves both ways. It brings it in and carries it out in waves, which we're going to look at that. So hang tight. Okay, so in the basic form of things, okay, a wave is a disturbance that transfers energy through matter. Okay, which is we're going to call matter. We're going to use the word medium. Okay, so the wave is a disturbance that carries energy through a medium, okay, which is just matter. Okay, matter is solid, liquid, or gas, and it's around it's in everywhere we interact with it every day. Okay, so remember, the big idea here is that a wave transfers energy, does not transfer matter. It transfers energy through matter, okay, which we're going to call medium. So the energy that is transferred through the medium is just repeated vibrations, okay, back and forth movement of an object. Okay, so when we interact with waves, it's just repeated vibrations. Okay, I'm going to show you some examples of that in just a moment. All right, the matter that some waves travel through, like I said, is called a medium. Examples of media, which is the plural form of medium, okay, media, is earth, water, air, also known as solid, liquid, and gases, okay, the Holy Trinity. Everything is either solid, liquid, or gas. All right, so waves transport energy. There's that thing again. It transports energy, okay, not matter. It transports energy from one place to another. Okay, or it can transform energy from one kind to another. What does it mean to transform? Okay, so it can take the energy moving from one form and change or transform into the energy of another kind. Okay, we're going to show you examples of that. All right, here's an example. Waves transform the nuclear energy released from the sun into other forms of energy on the earth. So any kind of solar energy, all right? So when we have those solar panels, that's nuclear energy from the sun that we see that feels hot on us. It gets real hot outside. Okay, those solar panels, they take that nuclear energy and they transform it to what? Anybody remember? Remember? Electrical energy. That's right. All right. Some of you said it. Some of you just waited for me to say it. But either way, it's still correct. The nuclear energy from the sun is transformed into electrical energy when we use the solar panels. Okay, and that nuclear energy travels to us and is transformed by the use of waves. Okay, waves. All right. Okay, now how does light travel? What does that matter to us? Why am I using that as an example? All right. Well, let's go back to its very simplest form, okay? Have you ever been standing around a puddle or a little small body of water and you dropped a rock into that water? We'll say a pond. Okay, dropping a rock into a pond. Now, you know those ripples. At the very center where you drop it, the ripples start going outward in every direction. Okay, that disturbance that when you drop the rock in there, okay, that's called a wave. Those waves go out in every direction. Now, since that rock was being pulled toward the center of the earth because of gravity, okay, it's moving. Right? So if it's moving, then we know it has mechanical energy. Okay? Mechanical energy, so it's moving. Mechanical energy is the energy of moving. Okay? So that mechanical energy that the rock holds while you drop it when it hits the water, it transfers that energy, that mechanical energy, to the water. Okay, and it causes the water to move. Now it's not moving the water, it's moving the energy through the water. Now when that rock hit the water, the rock did, as in science terms, we say that the rock did work on the water. Okay, it gave it energy. It transferred energy from the rock to the water. Okay, so it did work. Okay, now when the waves splash, they carry energy away from the center where you drop the rock. Okay, now those waves do work on the water and anything floating in the water. So example, if there's a leaf sitting there and the rock was dropped close by and those ripples, those waves carry that leaf and move it further out, okay, then we say that those waves did work on the water. Okay, it transferred the energy to the leaf. Now, however, the matter, the water and the floating objects is not transferred with the energy. Now it looks like, now if you just look at it, didn't know any better, you think, okay, look, the water's shuffling outward, but that's not true. What's happening is energy is moving throughout that body of water, and the water is staying still. Okay, it's rising and falling to the wave, but it's not transferring the water. Okay, I'm going to show you the transverse wave. So that is the big idea of this slide. Waves transfer energy, not matter, from one place to another. Okay, waves move through the medium. It doesn't move the medium. Okay, it doesn't transfer the medium. It just transfers the energy. Okay, remember that. All right, transverse waves. Now, unlike sound, which we established as longitudinal waves, light travels as a transverse wave. Okay, now a transverse wave is a wave in which the particles of a medium, the mediums that matter, move at a perpendicular, okay, you might know what perpendicular means. It means at a right angle, a 90-degree angle, to the direction that the wave is traveling. Now that sounds highly scientific, but what it's saying is that the particles travel in an up and down motion while the waves move across it. Okay, so like I said, that water, as the energy moves through that medium, okay, the water, it causes the water to rise up and go down, up and down, up and down. Now the medium moves there, but it's not moving it side to side. It's not causing it to flow outward. It's just transferring that energy. Okay, it's like if you would do like a dance move, do your hand in a wave. I know you can't see me, but I'm doing the wave right now with my hand, and it's going up and down, up and down, up and down. Now my hand is moving up and down, but it's not moving outward. The energy is moving through my hand to my arm, to my elbow, up to my shoulder, and eventually out of my body. But my arm and hand stay in the same space. You try. Okay, just move your hand up and down like in a wave, or put your hands together, lock your fingers, and then go up and down. Everybody knows that move. Okay. Now the word transverse means moving across. Okay, that's where we get transverse wave. It's because the wave is just moving across the medium. It's not moving the medium. It's just moving across it. It's just using it as a highway. Okay, it's moving. So an example of this is a water wave, like we talked about just a minute ago. Shaking a rope, moving up and down, you know, like you're doing a whip. You're doing a whip, or like S waves, which come from an earthquake. Okay, earthquake causes very big waves, and it causes what we call S waves, seismic waves, and it causes things to move on the earth. But probably the one you're most familiar with is shaking that rope. I mean, if you've ever, done like in a whip fashion with the rope, if you slow that down and you look over here to the right, like if you look over here, if you shake that rope, you have a low point and a high point, low point and a high point, low point and a high point. It's the same way if you do your hand, if you do your hand in a wave, you got a low point and a high point, low point and a high point, right? Okay, this is called a wave, a transverse wave, excuse me. You have a high point, a low point, high point, low point, and you see they're all equal. All right? So remember that as we're talking about transverse waves. The properties of a transverse wave. All right, now these are the parts of a remember, the transverse wave looks like this. Look here at the bottom. Transverse waves look like this. You got a high point, low point, high point, low point, and they're all equal. And you have a line that runs right through the middle to show you where this line would be if no energy was in there. Now, the highest point of this wave, we're going to call it the crest. It's known as the crest. Here are the crests right here. We got a crest here and a crest here. When that wave rises up to get to the highest point it's going to get to, that is known as the crest. Now, the opposite of a crest, at the highest point, is the lowest point, and that's called a trough. Okay, this is called a trough. It is the lowest point. It's the opposite of a crest. So we have crest real high. That means we have the troughs real low. Notice how I did my voice there, real low. Got the crest real high, trough real low. Okay, so troughs at the bottom, crests at the top. Now, this line that runs right through the center, this line tells you where the wave would be if there was no energy running through it. Okay, if there's no energy running through it, it's not moving. If you're not moving, you're in the rest position. Okay, if you ever go home after a long day of school, put your feet up, sit in the recliner, pull the chair out, pull your feet up, and you're not moving. That's called the rest position. Okay, this is also known as the point where the particles of a medium stay when there are no disturbances. There's no energy running through it. Okay, just like you at home. When you get home from school, there's no energy running through you. So you go and you sit down and you're not moving. All right? That's what this line represents. It is the rest position. No energy is running through it, so we're at zero. We're at nothing. We're just going to chill. This is the chill position. Okay? Now, another property is called a wave cycle. Now, this is one crest region and one trough region. So notice this picture. This is a wave cycle. A wave cycle goes up and down, then back to the rest position. So to get through one wave cycle, we start at the rest position. We go up one, down one, boom. There it is. Back to the rest position. Okay. Look at this wave over here. This wave's a little different. Okay. This wave goes up, down, and up. So from this point to this point is one wave cycle, right? Now, what do you notice about this wave and this wave? What is something that you notice about it? Well, this wave is a lot longer. It takes a longer time for that one to go from this rest position to this rest position, but this one is shorter. It goes whoop, 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 there it is. Boom, real short wave cycle. All right, now, when you put two or more of those wave cycles together, okay, you get what we know as a wave train. Whoop, whoop, wave train coming down. We got two or more wave cycles. So follow my pointer. We got a wave cycle up, down, up. There's one wave cycle. Up, down, up. There's another wave cycle. And then up, down, up. So we have three wave cycles. Okay. You can also count the crest. 1, 2, 3, or the troughs. 1, 2, 3. Right? So if you have two or more wave cycles, then you are on the wave train. Whoop, whoop, wave train. And most of the times that's what we receive all the time. So, yeah. All right. So we're going to keep moving on. All right. Now, we're going to get some more properties of a transverse wave. All right. Now, so we kept the same picture over here. So you could, the transverse waves are all the same, okay? All transverse waves have a crest, trough, rest position, all that stuff. Every transverse wave has that. Now, how do we measure, okay, how strong that wave is? Okay, how strong is that wave? Well, we're going to use the word amplitude to measure how strong it is. How strong is that wave? So amplitude. So that means that we're going to take the height from the rest position to the crest. Or we can take from the rest position to the trough. It is the maximum distance that the particles of a medium vibrate from their rest position. Okay, and that's a big, long definition, but I'm going to simplify it for you, okay? So you start at the, excuse me, at the rest position here. This line, remember, is sleeping. Note, this is the line that would be if no energy went through it, okay? So the rest position's here. So that's where we start. Now we measure it from the rest position to the crest. So this is called amplitude. That's how strong this wave is. Now, I don't have any units of measure, so it can't be like 2 centimeters or 1 nanometer or anything like that. So if I was to put units of measure here, then you could measure how much amplitude this wave has. Now you don't have to use the crest though. You can also use the trough because the crest and trough are identical. So you can either measure from the rest position to the crest, or you come over here from the rest position to the trough. Now it has to be to the center of the trough or the center of the crest. You can't come down here and measure, and you can't come over here and measure. You have to go from the rest position to the very highest point, or the rest position to the very lowest point, okay? Now, if we have a large amplitude, that means we have high energy. We got a lot of energy going on, okay? That means the distance between the rest position and the crest are bigger, right? So if that's bigger, we have more energy. Okay, now if we want to measure the wavelength, what's the wavelength? How long is it? Well, we have 2 identical points. Okay, we measure the distance between 2 identical points on different waves. So this would be from crest to crest or trough to trough. Okay, come over here, our picture. Okay, we see crest to crest right here. So we would take this, put our ruler here, and we would measure from here, from the very top point of this crest to the very top point of this crest. Okay, that gives us wavelength, as you see here. Now, just like amplitude, we don't have to use the crest. We can also use the troughs. So we come down here and we measure from the very, very bottom of the trough, and then we go over and we measure the very, very bottom of the other trough. That is one wavelength. That's all. Usually that's what we measure, wavelength. So it goes from here to here. Okay, and that's the same thing as measuring from crest to crest. You can also measure from trough to trough. Now, short wavelength, okay? So short wavelength means you have very high energy, okay? High energy. So if it's a very large amplitude, that means very high wave right here, and a short wavelength from here to here, that means that is extremely high energy, okay? The crests are real close together. But amplitude and wavelength are not related to each other. Okay, so remember that. They're not related. So you can have a high amplitude and a short wavelength, or you can have a low amplitude and a short wavelength. They're not related. One doesn't affect the other, is what I'm trying to say. Okay, so just remember that when we're measuring, or if I ask you if it's a high energy, well, what's the energy? Okay, they're not related to amplitude and wavelength, are not related to each other. Okay, so we're going to look at the parts of a transverse wave again. Okay, I just want to go over it and reiterate it with you again. So here's our transverse wave. Okay, here's our transverse wave. We got a crest, trough, crest, trough, high, low, high, low. Okay, so very first. Sorry, I gotta get out of the laser pointer. Okay, so here are the crests. Oh, sorry. All right. keeps jumping on me, sorry. So the very, very tops are known as the crest, and the very, very bottoms are known as the troughs. Now here, between the crest and crest are the wavelength, and you can also go from trough to trough. Now this one went from rest position to rest position. That's technically fine too, but I don't think I'll ever ask you to do that. We'll go from trough to trough or crest to crest. Now amplitude is, we start the rest position and we measure how the very tip top height to the crest, and that gives us amplitude. Or we can go from the rest position all the way down to the bottom of the trough. Now that's also amplitude. Remember, amplitude shows energy, okay? How much energy. The higher it is, remember that the crest and the trough are going to be equal. So if it's really, really high over here, it's going to be really, really low over here. So the higher it is, the more energy it has. The shorter it is, the less energy it has. Okay, so amplitude corresponds with the amount of energy carried by the wave. Now, another property of a transverse wave is frequency, right? Frequency. So frequency is the number of waves produced in a given amount of time in 1 second, okay? To break that down for you, okay, we have a period here, usually between trough, usually it's a wavelength, okay? So we measure frequency in hertz. Okay, have you ever heard of a hertz? Or like on your radio, you see MGH, like 30 megahertz, or so that's how frequent the wave passes a certain point. So let's say your antenna is a certain point, all right, on your car. If anybody has an older car, they have a metal antenna sticking up. All right, so that's your point of reference. That's how many times, that's where we're going to measure how many times a wave hits that one point, okay? So if it hit it, if that wavelength, it was 1 wave per second, that would be 1 hertz, okay? So if this wavelength right here, let me get my laser pointer. So if this wavelength right here, okay, see how short it is between trough to trough? The wavelength's really, really short. So that means a lot more waves would hit that point, that antenna. See how it's really short? So if this wave was moving and then moving out this way, okay, then that means a lot more waves would hit that antenna. We call that a high frequency wave. That means it has more hertz. Okay, high frequency equals high energy. Now, if we look at this picture down here, it's the opposite. Look at how long that wavelength is. So if it's a long wavelength, that means that if your antenna is right here and that wavelength's moving, that means only a few wavelengths would hit that antenna. So we call that a low frequency wave. Low frequency, all right? All right, now the time it takes to complete 1 full cycle, remember that 1 full cycle, we go from rest position, up, down, back to rest position. All right, that time it takes to complete 1 cycle, we call that a period. All right, and it's measured in seconds. So there. As frequency increases, wavelength decreases. Okay, this right here. So if you look back here, okay, as frequency increases, so if the frequency increases, means the wavelengths are really short. Okay, they're going down. Okay, the wavelength's really short at a high frequency. Now, when we start lowering the frequency, all right, frequency. Let me back up for a second. Frequency. What does that word frequency mean? Well, it comes from the word frequent. We all know what frequent means, correct? It's something that happens in a period of time. How often does it happen in a period of time is how frequent something happens. If you go to McDonald's twice a week to get a Big Mac, right? Then that's how frequent you go. You go twice a week. We wouldn't call that frequent, all right? Or I guess we would call it frequent. I mean, a lot of people don't eat that a lot, but and so that's the frequency that you go to McDonald's to get a Big Mac, okay, 2 times a week. Now, that's frequency, okay, is how much is done in a given time. Now, a high frequency, that means very short wavelength. A lot of waves pass through in a short amount of time. That's a high frequency. Now, if we do the opposite of this, if frequency decreases, then wavelength will increase. Okay? So it's just the inverse. Look at this second one. As we have a wavelength, a long wavelength here, okay? I mean, a low frequency wave, that means not a lot of waves are hitting this point. So our wavelength, our frequency has decreased. Then our wavelength has increased. That means we have a long wavelength. Long wavelength, low frequency. Short wavelength, high frequency. And you can look at this chart over here. Okay? So the amplitude is going to be about the same. The amount of energy is the same. But how frequent is it hitting that one position? Look at this wavelength. You have a rest position, down, up, rest position. That's how long one wavelength is. Okay? Look at this wavelength. It's a lot shorter. So if it's shorter, that means we have more frequency. And look at this, it's very high frequency. Look how short those wavelengths are. Okay, those are very, very short. So that means a lot of waves are going to hit that point in a given time. Okay, so just remember that as we go move forward. Okay, you'll practice this over and over. And hopefully you can retain it. Okay, let me get my pointer back. All right, so if we say that this line, this rest position here is a 1 second. Okay, look at how many waves are in that 1 second period. Okay, so that period is 1 second. So which one of these would be more frequent, would have a higher frequency? Which one of these would have a higher frequency? You're right, this bottom, because the wavelengths are shorter. Look at the wavelengths up here, this long wavelength, so the frequency is a lot lower, okay? Which one of these waves have a higher amplitude? Well, actually they're both the same. If you would take a ruler and go here to here, it would be the same as here to here. So the energy is the same. The frequency is what's different in this picture, okay? So bring us to our summary. What do we want to remember from this? Waves transfer energy, not matter, okay, from one place to another. So when we talk about waves, we're just moving energy. We're not moving matter. We're just moving energy from one point to another. Now the matter can move up and down, but it's not actually moving from one place to another. The parts of a transverse wave are the crest, the trough, the rest position, the wave cycle, and the wave train, okay? Mainly the parts of the crest, trough, and rest position. Those are the big three. The other two are really properties, but still need to know what they are. The wave cycle is the one from rest position, crest, trough, back to rest position. And a wave train, wave train, is when you have 2 or more wave cycles. Now you can measure a wavelength from a transverse wave. You can measure it from crest to crest or trough to trough. The highest point to highest point or lowest point to lowest point. Amplitude is from the rest position to the crest or from the rest position to the trough. That's how we measure how much energy a wave has, okay? So to measure the energy of the wave, we measure from the rest position to the height or the rest position to the trough. Frequency of a wave is how frequent does it pass a given point in an amount of time, usually 1 second. Okay, so the number of waves produced in a given amount of time. So if we have a section and we say that's 1 second, how many waves are in that 1 second? Okay, that's the frequency. Now, this is just the first part of this unit. Hopefully you retain this. You can please feel free to go back and review any part of the video that you need to get notes, or if there's something you didn't quite understand, go back and watch it again. Help yourself. Thank you for participating in this video, and have a great day.